Now in this video we're going to do 8.2 B and C, which we're going to talk about finding the critical values we need for constructing confidence intervals and the specifics of actually constructing a confidence interval for a population proportion. So the technical formula for this is actually right here. This is going to give us the confidence interval for a population proportion, and is actually referred to one sample Z interval for coming up with a confidence interval. And all we're going to do is we're going to take our point estimate. So we take p hat plus or minus our critical value using the Z table or the normal distribution times the standard deviation of the proportion. Keep in mind the standard deviation of the proportion is the square root of p hat times 1 minus p hat all over n, and then take the square root. Now this can be found on the AP formula sheet. One of the things we should talk about is the standard error. The standard deviation of p hat is also referred to as the standard error. And by definition what it is when it's the result when the standard deviation of a statistic is estimated. So we are going to be estimating what we think the statistic is, in this case what p hat is. This is on average how much error we're going to have in our p hat estimation. So this right here is another way to say it, how close the sample proportion p hat will be on average to the true population proportion in repeated samples. So it's kind of like the error we have in p hat as we're trying to come up with the true p parameter for the population proportion. Let's formally talk about 8.2b, which is computing the critical values for confidence intervals, and then we'll construct the confidence intervals from start to finish. Here they want us to construct a 96% confidence example. Use table A, or we'll use the calculator to find the critical value for 96% confidence. Now keep in mind the formula we would have for the confidence interval is p hat plus or minus z star, that is a critical value, and then we're going to do times the standard deviation of p hat. How do we come up with, the question is, this critical value? Well, we've talked about it before. They are telling us assume the normal condition is met, and we can assume that independence is 2 for this case. So to find it, remember here is our normal curve. This is, if it's standardized data, that's the mean is at 0. Now to find the 96 confidence interval means that they want 96% of the area under the curve. So if this is 96% of the area, what I technically need to find though is I want to do the inverse norm calculation. So remember, inverse norm will tell me what this critical value is supposed to be right here. It'll give me that z star. So how do I use inverse norm on the calculator? Well, what you're going to do is you would actually just type the area we're looking for, the mean, and the standard deviation. And the critical value we're trying to find is the z-score technically. So the mean is going to be 0 and the standard deviation is going to be 1. What's the area under the curve? Again, this is where we have to be careful. We want it from here all the way down. Now we've accounted for 96% of the curve, which means 4% of it has to be shared within these two tails. Well, if you take 4% and cut it in half, that's where we're talking about 2%. So we have to tack on an additional 2%. So we really want to find 98% of the area under the curve. So we can actually write that in our formula here. And this is all you need to type into the calculator. When you do that, you're going to get the critical value of 2.05. And remember, all this critical value is, it's the z-score. And the z-score means how many standard deviations we are from the mean. So we're technically a little over 2 standard deviations from the mean. So how does the confidence interval work? Well, you take that we're about 2 standard deviations away from the mean, and you times it by the standard deviation. So you're going to take your estimate of where we think the mean is, and we're going to add and subtract from it. In this case, we would be about 2 standard deviations on both sides of it. So let's go back to Mrs. Smith's class of the SRS they took of 102 pennies. Remember, they found that 57 of those pennies were more than 10 years old. So let's calculate and interpret a 99% confidence interval for them. And we're going to say P is the true proportion of pennies from the collection that are more than that. Let's compute p hat. So the proportion of pennies that are more than 10 years old in our sample is p hat, and that was a 57 over 102, or p hat is 0.559. Now let's find the critical value for it. I'm going to do a quick sketch. We are doing a 99% confidence interval. So a 99% confidence means we want 99% of the curve. Again, we have to be thoughtful about this in that we have two tails sitting out here, and we have 1% left over. So if you cut 1% in half, it's 0.005. So what we need to find in terms of the inverse norm for this is we can do it actually one of two ways. I'm going to show you a different way I did it this time. For the critical value, it's the point of the area under the curve. I did it to the left this time. So let me show you what I did. Is we know here this blue section is 0.005. So I said, give me this critical value right here. And I used just that little area. So I did inverse norm of this little area of 0 and 1. And it gave me a z-score of negative 2.567. Well, folks, a normal curve has perfect symmetry. So this z-score is going to reflect this z-score. This one is going to be the negative. This one is going to be the positive. So I actually can use this method and actually realize it's a positive value. So just a different way to think about it. Okay, now for the confidence interval, let's actually go ahead and put in the formula. So there's our formula. Our p hat is literally just going to be our 0.559. Our n in this case is 102, and our z critical value is 2.576. So if we just substitute that in, and we carefully simplify it, we're going to get it's 0.559 plus or minus this value. Let's do the plus or minus, and if we do that, we're going to come up with our confidence interval. Now, when you're asked to construct a confidence interval, you can't stop here. You will not get full credit. They want you to state this in its vocabulary terms and what it means. So you must, whenever they say construct a confidence interval, you must end it with the definition. And here's what we're going to say. We are 99% confident that the interval from 0.432 to 0.686, this right here, captures the actual proportion of pennies in the collection that are more than 10 years old. And we are done computing the confidence interval. Now, B is a good follow-up question. Is it plausible that exactly 60% of all the pennies in the collection are more than 60 years old? Is that a valid thing to actually say? Well, folks, we just constructed a confidence interval of where we think the true population proportion is. We think the true population proportion is somewhere in this range. So is it possible it's at 60%? Absolutely. 60% falls in between the 43% and the 68%. So for this, we're going to say yes. Since 0.6 is included in the confidence interval, it's plausible that 60% of all the pennies in the collection are more than 10 years old. Okay, let's wrap this up with here. Find the 95% confidence interval. What happens to the interval as the confidence decreases? Keep in mind this interval was at 99%. So if we find the 95% for it, we can go ahead and do that. When you do, all we have to do is come up with a different critical value. So here's what it's going to look like. The only adjustment we make is the critical value changes. The z-score, if you think about it too, this should be logical. For 99% of the curve, the z-score was out here. If I went less of the curve, the z-score is actually going to move in. So notice the z-score went from the 2.56 to 1.96. Well, if you crunch this out, what you're going to end up getting is our confidence interval changes to here. So this used to be at 43%, now it went to 46. It used to go up to over 68, now it's only going up to 65. So it gets smaller. So as we are less confident in our interval, the numbers get smaller. So this is a smaller range because we're less confident that we have the true population proportion in here. Now, would we change our answer to part B here? That that saying exactly 60% are in here, we'd come back and say, sure, it's still plausible because 60% is still within that range.